You've probably heard that the most violent events in the sky, the exploding stars and the colliding black holes, are simply the brightest things there are, and that with a big enough catastrophe you could always go brighter still. That is almost right. But it is wrong in a way that turns out to be one of the strangest facts in all of physics, because the universe does have a maximum brightness. There is a hard ceiling on how much power anything can release, anywhere, ever, and it is not set by how much fuel you have or how clever you are. It is woven into just two numbers, the speed of light and the strength of gravity, the same two numbers that built the carbon in your hands and hold your every atom in place. Nothing in all of creation can shine past it. So why does this limit exist, and what is the universe hiding on the far side of the brightest possible thing? Make yourself comfortable and get cozy. Subscribe if you haven't and stay with us, because where this ceiling comes from is stranger than any theory you've heard. Let us get into it. Part 1. The invisible loudest sound. Somewhere in the quiet swamplands of Livingston, Louisiana, just before 5 in the morning local time on September 14th, 2015, there is a machine sitting in the dark, listening. It does not look like much from the outside. 2 long concrete tunnels stretch away from a central building, each one running in a perfectly straight line for 4 kilometers, meeting at a right angle like the corner of an enormous invisible square. Inside those tunnels there is almost nothing at all. The air has been pumped out until what remains is one of the emptiest spaces ever created by human hands, emptier than most of the space between the planets. And down the center of that emptiness, a single beam of laser light travels back and forth, bouncing between mirrors that hang in absolute deliberate stillness, suspended so carefully from delicate fibers that they are, for all practical purposes, floating. This machine has one job. It is waiting for the shape of space itself to change, and on this particular morning, after years of waiting, it is about to succeed. Let me set the scene before we go any further, because the thing that is about to happen is so strange that it helps to slow down and feel the contrast. Right now, as that laser hums in the dark, the universe seems calm. The stars are doing what stars do. The Earth is turning. The people who built this machine are mostly asleep or just waking or drinking the first coffee of a long day. Nothing in the world feels dramatic, and yet, hurtling toward this quiet morning at the speed of light, having travelled for more than 1 billion years across the dark, is the aftershock of the most violent event that human beings have ever managed to measure. Here is what you need to understand from the very beginning, because it is the seed of everything we're going to explore tonight. The event that is about to arrive made no light. None. Not a flash, not a glow, not a single photon that any eye or any telescope could ever have caught. If you had been floating in space right next to where it happened, staring directly at it, you would have seen nothing but the ordinary darkness. And yet, as we will see, for a few thousandths of a second this silent, lightless event was more luminous, released more power than every single star in the entire observable universe added together. Brighter than all of them combined and completely invisible. Hold on to that contradiction. It is going to follow us all the way to the end. So what was the machine actually waiting for? It was waiting for a gravitational wave. And to understand what that is, you have to go back to a prediction made almost exactly 100 years earlier by a man working with nothing but a pencil and the inside of his own head. In 1915, Albert Einstein finished his general theory of relativity, and it carried with it an idea that even Einstein found a little hard to believe. The idea was that space is not a fixed, empty stage on which events play out. Space is more like a fabric, a flexible thing that can bend, stretch, and ripple. Mass and energy tell that fabric how to curve, and the curving of that fabric is what we feel as gravity. The Earth orbits the Sun not because of an invisible rope pulling on it, but because the Sun has made a kind of valley in the fabric of space, and the Earth is rolling around the inside of that valley. Now, if space really is a fabric that can bend, Then a natural question follows. What happens if you shake it? Take something with enormous mass and whip it around violently enough, and the theory says you should send ripples outward through the fabric of space. The same way dropping a stone into a still pond sends ripples across the water. Those ripples are gravitational waves. They are not waves travelling through space. They are waves of space moving outward, gently stretching and squeezing everything they pass through. And the reason it took us a full century to catch one is that these ripples are absurdly, almost insultingly faint by the time they reach us. Einstein himself doubted we would ever build anything sensitive enough to detect them. To give you a sense of how faint, consider what that machine in Louisiana was actually measuring. As a gravitational wave passes through, it lengthens one of those 4-kilometre tunnels and shortens the other, just slightly, and then reverses over and over in the rhythm of the wave. The amount by which the tunnels change length is the entire game, and that amount, for the wave that arrived on that September morning, was about 1/10,000th of the width of a single proton. Let me say that again, because the number is so small it tends to slide right past you. The detector measured a change in length thousands of times smaller than the nucleus of an atom, across a distance of 4 kilometres. It is the equivalent of measuring the distance to the nearest star and detecting a change the width of a human hair. That is the level of stillness, of precision, of obsessive care that went into building this thing. And it was not one machine, it was two. One in Livingston, Louisiana, and an identical twin nearly 2,000 miles away in Hanford, Washington. They were built as a pair on purpose, because a signal this faint could so easily be a trick of the local environment, a passing truck, a tiny earthquake, a gust of wind, a fluctuation in the equipment. But if the exact same pattern showed up in both detectors, separated by half a continent, within the few thousandths of a second it would take a wave travelling at light speed to cross the gap between them, then it was not a truck. Then it was something that had swept across the whole Earth from outside. At 9:49 and 45 seconds, coordinated universal time, it arrived. First at Livingston, then about 7,000ths of a second later at Hanford. The same shape, the same rising note, a signal that swept upward in pitch, faster and faster, and then stopped. Scientists later gave it a name, the way you would name a storm or a comet. They called it GW 150914. The letters stand for gravitational wave. The numbers are simply the date, written in the compact way scientists like. The year, the month, the day. The first one, the day, after 100 years of waiting, that we finally heard the fabric of the universe move. And here is the detail I want to leave you with as we end this first part, because it is the doorway into the whole rest of our journey. When the researchers converted that signal into something they could listen to, when they took the rise and fall of the stretching of space and turned it into an actual sound wave they could play through a speaker, it lasted about 2/10ths of 1 second, a fifth of a second, shorter than a single heartbeat, a soft, low thump that slides upward at the very end, the kind of sound you might make by running your thumb quickly up the low strings of a piano. Researchers started calling it the chirp. Think about that. The most powerful event ever recorded by our species, the release of more power than all the stars in the sky, arrived at the most sensitive instrument ever built, as a sound shorter and gentler than a bird call, the loudest sound the universe can make, and it is silent. We did not hear it with our ears. We did not see it with our eyes. We felt it, just barely, as the faintest possible shiver in the shape of space, smaller than the heart of an atom. It is worth pausing on just how unlikely it was that we ever caught this at all, because the catching is its own small miracle. For 100 years after Einstein wrote down the prediction, gravitational waves lived only on paper. Einstein himself went back and forth on whether they were real or merely a mathematical artifact of his equations, and even when he believed in them, he assumed they would forever be too faint to detect. Generations of physicists agreed. The signal was simply too small. To measure a change in length 1/10,000th the width of a proton, you have to build a machine quieter than almost anything else on Earth. A machine that can ignore the rumble of distant traffic, the breaking of ocean waves on a coastline hundreds of miles away, the faint seismic breathing of the planet itself, the random jitter of the atoms in its own mirrors. Every one of those disturbances is larger than the signal. Building an instrument that could pick a real gravitational wave out of that ocean of noise took 50 years of patient, stubborn, often doubted work by thousands of people, many of whom spent entire careers on it without ever knowing whether the thing they were chasing could be caught. And then there is the matter of timing, which still gives me a kind of pleasant chill. The two detectors, in Louisiana and in Washington, are separated by about 3,000 kilometers. A gravitational wave traveling at the speed of light crosses that distance in about 7/1000ths of a second. So when the signal showed up first in Louisiana, and then almost exactly 7/1000ths of a second later in Washington, that tiny delay was the fingerprint of reality. It was precisely the lag you would expect from a wave sweeping across the Earth from one particular direction in the sky at exactly light speed. No local truck, no electrical glitch, no equipment fault could fake that. The delay between the two machines was the universe signing its name. After a century of waiting, the signature was unmistakable. So what exactly was making that sound? What could possibly be violent enough to shake the fabric of the entire universe, and yet quiet enough to give off no light at all? The answer involves two of the strangest objects in all of physics, a piece of arithmetic that refuses to add up, and a number so large that, by the end of tonight, it is going to force us to ask a question almost nobody ever thinks to ask. Not how bright can something be, but whether there is a limit, written into the universe itself, on how bright anything is ever allowed to get. Let us follow the sound back to its source. Part 2. 3 Missing Suns. To find the source of that chirp, we have to travel a very long way and a very long time away from that quiet morning in Louisiana. The signal that arrived in 2015 had been travelling for roughly 1.3 billion years. That means it left its source before complex life had crawled onto land, back when the most advanced living things on Earth were simple cells floating in the sea. While that ripple was crossing the dark, every dinosaur that would ever live was born and died, the continents rearranged themselves, and our entire human story, from the first stone tool to the machine that finally caught the wave, played out in the last little sliver of its journey. And what made it? 2 black holes. Not one, 2, locked in a death spiral around each other. Let us take a moment with black holes, because they sit at the centre of everything tonight, and because they are the key to that contradiction we keep circling, the idea of an event with overwhelming power and no light. A black hole is what you get when you take a large amount of matter and crush it into a space so small that its gravity becomes inescapable. The fabric of space around it does not just dip into a gentle valley the way it does around the sun. It plunges into something more like a bottomless funnel, and there is a boundary around a black hole, a kind of point of no return called the event horizon. Anything that crosses it, including light itself, can never come back out. That is the whole reason these objects are black. They are not dark because they are cold or empty. They are dark because they are so violently massive that they trap their own light. Light falls into them and never escapes to reach your eye. So now picture the source of our signal. 2 of these objects, 2 regions of trapped light and bottomless gravity, orbiting each other. One of them weighed about 36 times as much as our Sun. The other weighed about 29 times as much as our Sun. And they were not gently circling at a comfortable distance. They were whipping around each other faster and faster, drawing closer with every orbit, because the act of orbiting was itself shaking the fabric of space and bleeding away their energy as gravitational waves. The more they radiated, the closer they fell. The closer they fell, the faster they spun. The faster they spun, the more they radiated. It is a runaway process. a spiral that can only end one way. In the final moments, those two black holes were circling each other dozens of times every second, their surfaces moving at a substantial fraction of the speed of light, and the space around them was ringing like a struck bell. And then, in a final instant, they touched and merged and became a single, larger black hole. That final plunge and merger is the violent heart of the chirp. That is the rising note. The pitch climbs because the orbit speeds up, and then it cuts off because suddenly there are no longer two objects orbiting. There is just one, settling down, ringing softly, going quiet. Now, I want to show you the piece of arithmetic that, the first time you really see it, should stop you in your tracks. We had two black holes. One was 36 solar masses. One was 29 solar masses. Add those together, and you expect the final black hole to weigh 65 times the mass of the Sun. 36 plus 29 is 65. That is just basic addition. But when the scientists measured the mass of the final black hole, the one left over after the merger, it did not weigh 65 solar masses. It weighed about 62. 3 solar masses were missing. Let me make sure that number lands, because it is easy to read past it. 3 times the mass of our Sun simply was not there anymore. The Sun is not a small thing. You could fit well over 1 million Earths inside it, and 3 of those, 3 entire suns worth of material, had vanished from the ledger between the start of the merger and the end of it. So where did it go? It did not go anywhere. It stopped being matter and became energy. This is the most famous equation in all of science, finally showing its true face. Energy equals mass times the speed of a light squared. Einstein's equation tells us that mass and energy are 2 forms of the same thing, and that a tiny amount of mass, if you could fully convert it, contains a staggering amount of energy, because you are multiplying it by the speed of light squared, which is an enormous number. The bombs that ended the Second World War converted less than a single gram of matter into energy, less than the mass of a paperclip. And here, in this merger, 3 entire suns were converted into pure energy and released not as light, not as heat, but as a violent ringing of space-time itself, a tsunami of gravitational waves rolling outward in every direction. This is the answer to our contradiction. The event gave off no light because the energy never took the form of light. It took the form of gravity, of moving space. All of that power, 3 suns turned to energy, poured out as a shockwave in the fabric of the universe. And now we come to the number that this entire video is built around. How much power are we actually talking about? When physicists worked out the rate at which that energy was released at the very peak of the merger, in the final thousandths of a second, they found something almost impossible to believe. At its peak, the collision was radiating energy at a rate of about 3.6 times 10 to the 49th watts. That string of words probably does not mean much yet, so let me translate it into something you can feel. A watt is just a measure of power, of energy per second. A bright household light bulb is about 100 watts. The entire sun, pouring out light and heat in every direction, shines at about 400 trillion watts. And this merger, for a few thousandths of a second, was putting out energy at a rate equal to roughly 10,000 trillion suns. Another way physicists describe it is that, at the peak, the event was shedding about 200 suns worth of energy every single second, even though the whole event only had 3 suns of fuel to spend, which tells you the whole thing was over in a flash. But here is the comparison that truly matters, the one I want you to carry with you. Take every star in our galaxy, the entire Milky Way, hundreds of billions of stars. Their combined light, added all together, is still more than 100 billion times fainter than the peak of this single merger. And now, take not just our galaxy, but every galaxy in the entire observable universe, 2 trillion galaxies, each with its hundreds of billions of stars. Add up all of that starlight, every sun that we could ever in principle see, all shining at once. For a few thousandths of a second, this one event, these two black holes becoming one outshone the combined light of the entire visible universe by a factor of more than 10, and it was silent, and it was invisible, and it passed straight through you. I mean that literally. When that wave finally reached Earth in 2015, it did not just register in the machine. The machine is simply the only thing precise enough to have noticed. The wave passed through the entire planet. It passed through the building, through the scientists who were asleep, through the oceans and the mountains. It passed through your television, through your phone, through your own body, very slightly stretching and squeezing you, your bones, your heart, the space between your atoms by an amount far too small to feel. The most violent event our species has ever measured reached out across 1.3 billion years of darkness, and it touched you, personally, and you never knew. You felt nothing. You could not have. And yet it happened. There is something worth dwelling on in that idea of mass becoming energy, because it is so central to everything that follows, and because it is easy to say the words without feeling them. When we say 3 suns of mass were converted to energy, we're not saying the material was scattered, or vaporized, or thrown outward as debris. We are saying it ceased to be matter at all. The stuff of 3 entire stars stopped existing as stuff and became pure motion in the fabric of space. There is no ash left behind from that conversion, no glowing cloud, no wreckage. The energy left the scene entirely as a wave, and what remained was simply a black hole slightly lighter than the sum of its parts. It is the most complete transformation of matter into energy that the universe knows how to perform. A star fusing hydrogen, like our sun, converts less than 1% of the mass involved into energy. A merger like this one converts a far larger fraction, and it does it not over billions of years, but in a final fraction of a second. It is the most efficient and the most violent release of energy that ordinary gravity can produce. And I want to underline the strangeness of the form that energy took, because we will spend the rest of the night chasing brightness, and this was a brightness with no light. Every other powerful event you can name announces itself with light. A supernova floods its galaxy with photons. A quasar blazes across the universe. Even an ordinary fire glows. But this merger, the most powerful event we have ever measured, produced essentially no light of its own at all. 2 black holes have no surfaces to shine, no gas to ignite, nothing to glow. All of that staggering power went into the one channel that does not light up the sky. It went into shaking space. And that is why, for all its overwhelming power, you could have been watching the exact patch of sky where it happened, with the finest telescope ever built, and seen nothing change. The brightest thing is not always the one you can see. Sometimes the brightest thing is the one that passes straight through you in perfect silence. So we have our source. 2 black holes, 3 missing suns, and a flash of silent power brighter than all the stars in the sky. And this is the moment where most people would simply stand back and say, well, that is the most extreme thing in the universe, and leave it there. But I want to ask a stranger question. The question that turns this from a story about one event into a story about the structure of reality itself. Is this the most powerful thing that can possibly happen? Or could there be something even brighter, even more violent somewhere out there? And if we keep climbing, looking for brighter and brighter things, do we ever reach a top? To answer that, we have to start at the very bottom, with something a great deal humbler than a black hole. We have to start with a candle. Part 3. The ladder begins. Imagine you're sitting in a dark room, and in front of you there is a single candle. The flame is small and steady. It throws a soft, warm circle of light onto the walls, enough to read by if you hold the page close, enough to see the face of someone sitting across from you. It is, in every sense, a gentle thing, and it is the perfect place to begin our climb, because a candle is something your body understands. You know how warm it is. You know how far its light reaches. You know that if you cup your hand around it, you can almost hold all of its power in your palm. So let us measure it. A single candle flame radiates light at a rate of very roughly 1 watt. The exact number depends on the candle, but 1 watt is a good, honest, human-sized place to plant our feet. 1 watt. Remember that, because every step we take from here is going to be a multiplication, and a candle is rung number 1 on a ladder that is going to climb so high that, by the end, the numbers stop having any meaning your imagination can hold. We are going to need this candle. When the numbers get monstrous, I want you to be able to come back here, to this quiet room, and remember that all of it is just candles, stacked higher and higher. Take 1 step up. Replace the candle with a bright household light bulb, the kind that lights an ordinary room. That bulb runs at about 100 watts, so already, with a single small step from candle to light bulb, we have multiplied our brightness by a factor of 100. 1 bulb is worth 100 candles. That feels reasonable. You can picture 100 candles. It would be a lot of candles, an entire table covered in them, a small fire hazard, but you can hold the image in your mind. 100 little flames, all flickering, equal to 1 steady bulb. Now let us take a bigger step and leave the room entirely. Step outside, into a city at night. Think of every light you can see. The streetlights marching down the avenue, the headlights of the cars, the glowing windows of the apartment towers, the billboards, the shop signs, the floodlights over the stadium across the river. A single large city, lit up against the dark, is pouring out light at a rate of perhaps hundreds of millions of watts. We have left the candle far behind. To match a single city, you would need hundreds of millions of candles. More candles than you could light in a lifetime. More candles than there are people in most countries. And we're still, in the grand scheme of tonight, practically at 0. Let us take the largest human step we can take. Forget 1 city. Add up every power source that the entire human species controls, every power plant on Earth, every coal furnace and nuclear reactor and hydroelectric dam, every wind turbine and solar farm, every car engine and jet engine and rocket, every device that human beings have ever switched on, all running at once, the total output of our entire global civilization. Add all of it together, and you arrive at a number of around 10 trillion watts. Sometimes people round it up to roughly 20 trillion. 10 to the 13th watts, give or take. That is the full brightness of humanity, the entire energy footprint of 8 billion people and all of their machines burning together. I want you to sit with that number for a moment, because it is the high watermark of everything we have ever built. 10 trillion watts. It sounds enormous, and in human terms it is. It is the sum of all our industry, all our cities, all our power, and we are going to leave it behind almost immediately and never look back, because compared to where we are going, the entire output of human civilization is a rounding error. It is barely a step up the ladder. It is, in fact, a number we will pass and forget within the next 2 minutes of this story. Notice what is happening as we climb. Each step is not adding a little. Each step is multiplying. From candle to bulb times 100. From bulb to city times millions. From city to civilization, more multiplying still. This is the strange thing about brightness, about power, about luminosity. It does not climb in gentle, even steps. It climbs in leaps, each one dwarfing the last, and that means our intuition, which is built for adding things, is completely the wrong tool for the journey ahead. Your mind wants to imagine the next step as a bit bigger than the one before, but the universe does not work in a bit bigger. It works in unimaginably bigger, again and again and again, and we're going to have to keep multiplying until something finally stops us, if anything stops us at all. So let me give you a way to keep your footing, because we are about to leave the Earth, and once we do, the honest numbers become so large that you will need an anchor. The anchor is this. We're going to keep track of our climb in factors of 10. Every time I say we go up by a factor of 10, I mean the number grows a 10th zero longer. 10 becomes 100, 100 becomes 1,000, 1,000 becomes 10,000. It does not sound like much each time, but 10 steps of a factor of 10 is a factor of 10 billion. 20 steps is a factor of 1 followed by 20 zeros, and tonight, before we are done, we're going to take more than 50 of those steps up from our single candle. 50 multiplications. That is the size of the ladder we are standing at the bottom of. And here is what I find genuinely beautiful about starting this way, in the dark, with one small flame. Everything we're about to encounter, the sun, the exploding stars, the quasars devouring worlds, the colliding black holes that shake the universe, all of it is made of the same stuff as that candle. It is all just energy being released. The flame on the candle is atoms recombining, releasing little packets of energy as light. The sun is doing something grander, fusing atoms together in its core, but it is still, at bottom, releasing energy. The exploding star, the feeding black hole, the merger, all of it. There is no special magical ingredient that appears halfway up the ladder. It is the same physics, the same release of energy, the same kind of light, all the way up. The candle and the colliding black holes are cousins. They differ only in degree, which makes the question we are chasing even sharper. If it is all the same kind of thing, all just energy being released, then why should there be a limit at all? A candle is 1 watt. A merger is 10 to the 49th watts. We have just watched brightness leap from a single flame to something that outshines the visible universe. If it can leap that far, why can it not leap further? Why not 10 to the 60th watts? Why not 10 to the 100th? What, in a universe that seems so willing to multiply, could possibly say no? Let me give you one more handhold before we leave, because the way humans misjudge these climbs is itself worth understanding. Our minds evolved to deal with quantities we can count on our fingers, or at most quantities we can picture: a herd of animals, a basket of fruit, a crowd in a square. When a number grows past a few thousand, our intuition quietly gives up and just files it under many. And that is fatal on a journey like this one, because the difference between many and many is where the entire story lives. The gap between a supernova and a black hole merger is not the gap between 1,000 and 2,000. It is the gap between 1 and a trillion. If you let your mind flatten those into the same vague bigness, you will miss the whole point. So every time I give you a new number tonight, I am going to try to tie it to something you can actually feel. A candle, a sun, a galaxy. Because the felt comparison is the only way to keep the climb honest. The numbers alone will lie to you by sounding similar. The comparisons will tell you the truth, and here is a comparison to carry upward. We have already climbed from a single candle to the entire output of human civilization, and that felt like an enormous leap. It was. It was a factor of about 10 trillion. But the next single step from all of human civilization to one ordinary star, our own sun, is a leap roughly as large again. One sun outshines everything our species has ever built by about the same factor that our whole species outshines a fraction of a candle. So one step into the sky, and we have already matched in a single object the entire climb we just made through all of human power. That is the rhythm of what is coming. Each step is not a little higher. Each step is the whole previous journey, all over again, stacked on top. That is the question. And to find the answer, we have to leave the warmth of this room behind and step out into the cold, where the truly bright things live. We have to go to the stars, because it is among the stars that we will meet, for the first time, something pushing back, something that does not want to get any brighter. The first hint that the ladder, for all its willingness to climb, might just have a top after all. Let us go and meet a star that is trying and failing to shine too brightly for its own good. Part 4. The Stars and the First Ceiling. The sun is so much a part of our lives that we almost never think of it as an object. It is just the sky being bright. But it is an object, a single ball of glowing gas, and it is the next great rung on our ladder. Our sun radiates energy at a rate of about 3.8 times 10 to the 26th watts. Let me put that against our anchor. A candle is 1 watt. The entire output of human civilization is around 10 trillion watts. 10 to the 13th. The Sun is 10 to the 26th. That means the Sun is to all of human civilization roughly what all of human civilization is to a small fraction of a candle. The single nearest star outshines everything our species has ever built by about the same factor that our entire species outshines almost nothing at all. And the Sun does this not for 1,000th of a second, like the merger, but steadily, calmly, for billions of years. It has been pouring out this torrent of light for over 4.5 billion years already, and it has enough fuel to keep going for roughly another 5 billion. Every second, the Sun converts about 4 million tons of its own mass into energy, fusing hydrogen into helium in its core and releasing the difference as light and heat. The same trick the black hole merger pulled, mass becoming energy, but done gently, patiently, sustainably, instead of all at once in a final catastrophe. The warmth on your face on a summer afternoon is the arrival of that energy, 8 minutes after it left the surface of a controlled, billion-year explosion 93 million miles away. Now let us keep climbing, because the Sun, as enormous as it is a fairly modest star. There are stars far more massive and far more luminous. As stars get bigger, they burn hotter and brighter, and not just a little. A star 10 times the mass of the Sun can be thousands of times more luminous. And at the very top of the stellar world, there are monsters. Consider a star with the catalogue name R13601, which lives in a dense cluster in a neighbouring galaxy. It is one of the most massive and most luminous stars known, and it shines at several million times the brightness of our Sun. Several million suns bound up in a single star. That puts it at around 10 to the 32nd watts. We have climbed 6 more factors of 10 above our own Sun, just by going from an ordinary star to the brightest kind of star that exists. And here, for the first time on our journey, we hit something we have not seen before. We hit resistance. Because it turns out you cannot just keep building brighter and brighter stars forever. There is a point past which a star cannot go, a brightness it cannot exceed without destroying itself. And the reason why is one of the most elegant pieces of physics in this whole story, so let us slow down and really see it. A star is, at every moment of its life, a battle between 2 opposing forces. On one side there is gravity, the enormous weight of all that gas pulling inward, trying to crush the star down toward its own centre. If gravity were the only force at work, the star would simply collapse. But there is a second force pushing outward, and that force is the star's own light. This is a subtle and beautiful idea. Light is not weightless in its effects. Light carries momentum, and when it streams outward from the blazing core of a star pushing against the gas on its way out, it exerts a real outward pressure, a force physicists call radiation pressure. The light of the star is literally holding the star up, pushing outward against the crush of gravity. A star, for most of its life, is a perfect self-regulating standoff. Gravity pulls in, light pushes out, they balance, and the star is stable. But now think about what happens as a star gets brighter and brighter. The brighter it shines, the harder its own light pushes outward, and there comes a point, a specific brightness, where the outward push of the light exactly equals the inward pull of gravity. Climb even a little brighter than that, and the light wins. The star's own radiation begins to overpower its gravity, and it starts to blow its own outer layers off into space, shedding material, tearing itself apart from the inside out. It cannot hold itself together. The very light that makes it brilliant becomes the thing that destroys it. That tipping point has a name. It is called the Eddington limit, after the astronomer Arthur Eddington, who worked it out. The Eddington limit is the maximum brightness an object can sustain before its own light blows it apart, and it is the first ceiling we have met on our climb. After 3 parts of pure, joyful multiplication, candle to bulb to city to sun to hypergiant, here, finally, is the universe saying a word it has not said before. The word is enough. This is a genuine turning point in our story, so let me make sure we feel the weight of it. Up until now, brightness has felt free. It has felt like you could always have more, just by piling on more fuel, more mass, more energy. But the Eddington limit reveals something deeper. It reveals that brightness fights back. The very thing that makes a star shine, its light, is also the thing that limits how bright it can be. There is a kind of justice in it, almost a poetry. The more brilliant a star tries to become, the more its own brilliance works against it, until it can climb no higher. But, and this is crucial, the Eddington limit is what I would call a soft ceiling. It is real, but it is not universal. It depends on the mass of the particular object you're talking about. A more massive object has stronger gravity, so it can tolerate more outward light pressure before being torn apart, which means it has a higher Eddington limit. A less massive object has a lower one. So the Eddington limit is not a single number written across the whole universe. It is a sliding scale, a different ceiling for every object, set by how much gravity that object has to hold itself together. Pile on more mass, and you raise the ceiling. It bends, it gives, it is not the final wall. And that distinction between a soft ceiling that depends on the object and a hard ceiling that does not is going to become the heart of everything that follows. Because the question we are really chasing is not whether any particular star has a limit. Of course it does. The question is whether the universe as a whole has a limit. Is there a brightness that nothing can exceed, no matter how much mass you pile on, no matter how clever you are, no matter what kind of object you build? A ceiling that does not bend when you push on it? The Eddington limit is not that ceiling. It is just the first warning sign, the first hint that brightness is not infinitely free, that somewhere up ahead there might be a wall that does not move. It is worth lingering on why the Eddington limit feels so different from the wall we're ultimately chasing, because the contrast teaches you how to recognize a true, fundamental limit when you finally meet one. The Eddington limit is what you might call a limit of circumstance. It comes from a particular situation, a ball of gas trying to hold itself together while its own light pushes outward. Change the circumstance, pile on more mass, and the limit moves. It is real, but it is local and negotiable. It is the kind of limit an engineer runs into, the sort of thing you can design around if you're clever enough or have enough resources. A taller building needs a stronger foundation, but you can always build a stronger foundation. A brighter star needs more gravity to hold it together, but you can always add more mass. These are limits you push against and slowly overcome. A fundamental limit is a different animal entirely. A fundamental limit does not move no matter what you do, because it does not come from any particular circumstance. It comes from the structure of reality itself. The speed of light is the classic example. You cannot go faster than light not because we have not built a good enough engine yet, but because the limit is woven into the geometry of space and time. No amount of cleverness, no amount of resources, no better design will ever get you past it. It is not a wall in your path that you might one day climb over. It is the edge of the playing field. And the question that should be forming in your mind, the question that the rest of this video exists to answer, is which kind of limit governs brightness? Is the top of the ladder a limit of circumstance like the Eddington limit, something we could in principle outbuild? Or is it a fundamental limit, like the speed of light, an edge of reality that nothing can ever cross? Keep that distinction sharp, because everything turns on it. So we have learned something important. The universe does push back. Light limits itself. But we have also learned that this particular limit can be beaten simply by adding more mass. So let us do exactly that. Let us go and find the most massive, most violent, most luminous objects the cosmos has ever made, the dying stars and the feeding giants, and see just how far we can push past our own modest sun before we find a ceiling that will not bend. We're about to enter the realm of catastrophe, where stars explode and black holes devour worlds, and where the numbers are going to climb so fast that our candle will feel like a distant, almost forgotten dream. Part 5. When Stars Outshine Galaxies. When a truly massive star reaches the end of its life, it does not fade away quietly. It dies in the single most violent explosion that ordinary matter can produce. We call it a supernova. For most of its existence, the star held itself up by fusing lighter elements into heavier ones, releasing energy that pushed outward against gravity, exactly the standoff we talked about. But eventually the core fills up with iron, and iron is the end of the road. Fusing iron does not release energy, it costs energy. So the moment the core becomes iron, the outward push stops, the standoff collapses, and gravity wins all at once. The core implodes in a fraction of a second, the outer layers come crashing down onto it and rebound in a titanic shockwave, and the star tears itself apart in a blast that, for a few weeks, can be seen across the universe. How bright is a supernova at its peak? It reaches something like 10 to the 36th or 10 to the 37th watts. Let me translate that. A single exploding star for a few weeks shines with the light of billions of suns. It becomes, briefly, as bright as an entire galaxy. Think about that the next time you look at a faint smudge of a distant galaxy. Hundreds of billions of stars blurred together by distance. A single supernova, one dying star, can match that entire blur of light all by itself. When ancient astronomers recorded a new star suddenly appearing in the sky, bright enough to see in daylight, and then slowly fading over months, they were watching one of these. They were watching a single star for a little while shine as brightly as 100 billion of its neighbours, and there are even fiercer versions. There is a class of explosions, the superluminous supernovae and the supernova tied to gamma-ray bursts, that climb higher still, reaching brightnesses well above the ordinary supernova range. We have pushed several more factors of 10 up the ladder, from our brightest stable star to the death explosions of the largest stars, and we are still climbing. But supernovae are brief, and they involve ordinary exploding matter. To find the brightest steady lights in the universe, the searchlights that burn for millions of years, we have to go back to the black holes, only this time not colliding but feeding. When a supermassive black hole at the centre of a galaxy has a steady supply of gas falling toward it, that gas does not simply drop in quietly. It piles up into a vast swirling disk spiralling inward, and as it spirals it is compressed and sheared and heated by friction and gravity to absolutely staggering temperatures, millions of degrees, until the disk itself blazes with light so intense it can be seen clear across the universe. We call these blazing cores quasars. They are the brightest sustained objects in all of creation. Let me take you to one. Drift with me, in your mind, toward the most luminous quasar yet discovered, an object with the catalogue name J0529-4351. Approach it slowly and let the scale arrive in pieces. First, the black hole at its heart. It weighs about 17 billion times the mass of our Sun. Not 17 million. 17 billion. A single object as heavy as a small galaxy's worth of stars, crushed into a region of trapped light. Now see the disk of matter swirling around it. That disk is so large that it would not fit inside our solar system. It is wider than the orbits of all the planets. A whirlpool of superheated gas spanning a distance light itself takes days to cross. And it is screaming with light. The whole structure is so bright that it consumes as fuel a quantity of matter equal to our entire Sun every single day. Picture that. A star like our Sun, the thing that took 4.5 billion years to build, the thing whose light defines our days and seasons and whole existence, falling into this monster and being devoured as a single day's meal, and tomorrow another, and the day after another. How bright does all that make it? J0529 shines at roughly 2 times 10 to the 41st watts. That is more than 20,000 times the combined light of every star in our entire Milky Way galaxy. One object, 20,000 galaxies worth of light, pouring out steadily, not for 1,000th of a second like the merger, not for a few weeks like a supernova, but for millions of years, as long as the fuel keeps falling, it is the brightest continuously shining thing we have ever found. And here is the detail that ties it back to the ceiling we met in the last part. When astronomers studied this quasar, they found that it is feeding right at the edge of its own Eddington limit. It is shining as brightly as an object of its mass can possibly shine without blowing its own fuel supply away. It has pushed its soft ceiling about as high as a soft ceiling can go by piling on a truly absurd amount of mass, and yet 2 times 10 to the 41st watts. Hold that against where we are heading. The merger we started with, GW150914, peaked at 3.6 times 10 to the 49th watts. That means the most violent black hole merger we have ever measured was, for its brief instant, around 100 million times more powerful than the brightest steady quasar in the universe. The quasar burns for millions of years and outshines 20,000 galaxies. The merger lasts a fraction of a second and outshines the quasar 100 million times over. That is how much further up the ladder the merger sits. There is one more rung worth touching before we get there, and it is one of the strangest objects in the sky. A gamma-ray burst. When certain massive stars collapse, or when 2 neutron stars collide, they can release an enormous flash of energy focused into a narrow beam, like the light of a lighthouse rather than the glow of a bare bulb. For a few seconds, a gamma-ray burst can release on the order of 10 to the 52nd ergs of energy, and if you happen to be looking straight down the barrel of that beam, the apparent brightness is so high it is almost meaningless to compare it to ordinary stars. These are, second for second, among the most luminous events in the cosmos, brief beams of annihilating energy that we detect from billions of light years away. So let us take stock of how far we have climbed. We started with a candle at 1 watt. We are now in a realm where single events outshine entire galaxies, where black holes eat suns for breakfast, where dying stars flash with the light of billions of suns, and where beams of gamma rays cross the universe. We have multiplied our candle by a factor of more than 10 to the 49th. We have taken nearly 50 steps of a factor of 10 up from that quiet flame in the dark room, and at every step the universe has been willing to go higher. The Eddington limit slowed us down, but we beat it by piling on mass. Nothing has truly stopped us. The ladder has just kept climbing, and this is exactly the moment when a reasonable person concludes that there is no limit at all. We have gone from a candle to colliding black holes through 50 factors of 10, and the universe has said yes every single time. Why would it ever say no? Surely if you could just find an even bigger black hole, an even more violent collision, an even more massive object, you could go higher still. 10 to the 50th watts, 10 to the 60th, 10 to the 100th. Surely the ladder, having climbed this far, simply continues forever. Let me press on that reasonable conclusion a little harder, because it is exactly the kind of belief that feels like common sense, and turns out to be wrong, and those are the most interesting beliefs to overturn. The conclusion goes like this. We have climbed 50 factors of 10. At every single step the universe cooperated. We found bigger objects, more violent events, and the brightness obediently went up. The Eddington limit slowed us, but we simply added mass and sailed past it. So by straightforward extrapolation the ladder must continue. Find a bigger black hole, get a brighter merger, find an even bigger one, get an even brighter merger. There seems to be no reason the pattern would ever stop. Extrapolation is one of the most powerful tools in science, and here it points clearly upward, forever. But extrapolation has betrayed us before, and always in the same way. It betrays us whenever a brand new kind of limit, one that was invisible and irrelevant in the regime we were used to, suddenly becomes the thing that matters most. For most of history, people extrapolated that you could always go a little faster. Faster horse, faster train, faster plane. There seemed no reason it would stop, and then, as speeds climbed toward the speed of light, a limit that had been completely invisible at everyday speeds rose up and became absolute. The old pattern simply ended, not gradually, but at a hard edge that had been there the whole time, waiting, ignored, because nothing had ever gone fast enough to feel it. That is exactly the situation we're in now with brightness. We have been climbing in a regime where the ceiling was so far above us that it might as well not have existed. But we have now climbed so high, with the merger, that the ceiling is finally within sight, only 3 more steps up. And as we approach it, a limit that was invisible for the entire climb so far is about to become the only thing that matters. Except, it does not. And the reason it does not is the single most surprising turn in this entire story. Because somewhere just above the merger we started with, only a few more steps up from where we now stand, the universe stops. Not because we run out of mass to pile on, not because we run out of ambition or fuel or cleverness. The universe stops because of something built into the deepest structure of reality itself, a wall that does not bend when you push on it, a hard ceiling on how bright anything can ever be. In the next part, I want to show you that this wall exists, and then, after that, I want to show you the truly astonishing thing, which is exactly why it has to be there. Let us go and find the top of the ladder. Part 6. The wall that shouldn't exist. I want to start this part by convincing you of something that sounds completely reasonable, so that I can then show you it is wrong. Here is the reasonable sounding idea. In the universe, as most of us imagine it, there is no limit to how strong things can get. Take gravity. In the physics of Isaac Newton, the physics that ruled science for more than 200 years, and that still describes the falling of an apple and the orbit of the moon perfectly well, the gravitational pull between 2 objects depends on their masses and on the distance between them. Push them closer together, and the pull gets stronger. Push them closer still, and it gets stronger still. And here is the key point. In Newton's universe, there is nothing stopping you from pushing 2 objects arbitrarily close together. As the distance between them shrinks towards 0, the force between them grows toward infinity. There is no ceiling. The force can become as large as you like. By that logic, brightness should have no ceiling either. Brightness, luminosity, is just energy released per second. And if you can always concentrate more mass into a smaller space, and generate a stronger and stronger pull, and release energy faster and faster, then you should always, in principle, be able to make something brighter. The ladder we have been climbing should simply continue, forever, without a top. That is what Newton's universe promises. Infinite room at the top. And it is wrong. The real universe does not work that way. The real universe has a top. There is a maximum brightness, a maximum power, a maximum rate at which energy can be released anywhere, by anything, ever. And it sits at a value of about 3.6 times 10 to the 52nd watts. Let me place that number on our ladder so you can see how close we came. Our candle was 1 watt. The brightest steady quasar was around 10 to the 41st watts. The black hole merger that started this whole journey peaked at 3.6 times 10 to the 49th watts. And the absolute ceiling, the highest brightness the laws of physics permit, is 3.6 times 10 to the 52nd watts. Look carefully at those last 2 numbers, 3.6 times 10 to the 49th for the merger, 3.6 times 10 to the 52nd for the ceiling. The only difference is 3 factors of 10, 3 steps. The merger we detected, the first gravitational wave humanity ever heard, came within a factor of about 1,000 of the brightest that anything in the universe is allowed to be. Sit with that for a moment, because it reframes everything. We did not detect some modest, middling event, and then learn that, in principle, far off in the realm of theory, there is some unreachable maximum a googol times higher. No. The very first thing we ever heard, the first ripple in space-time we ever caught, was already pressed up against the ceiling of reality. It was already in the top 1,000th of everything that can possibly happen. When those 2 black holes merged, they were not playing in the foothills of what is possible. They were standing almost at the summit, knocking on the highest door there is. And that phrase, knocking on a door, is one I want you to hold on to because we are going to come back to it. When something reaches up toward this ceiling, it is not like a ball bouncing off a hard surface. It is more like a knock on a locked door. Something is on the other side of that maximum, some deeper truth about the universe, and every time a violent enough event climbs up toward the ceiling, it is rapping on that door asking to be let through. We have been knocking on that same locked door in one way or another for 100 years. By the end of tonight, I want you to understand exactly what door it is. But first, the obvious question: how can this be? How can a universe that was so willing to multiply, that took us up 50 factors of 10 from a candle without complaint, suddenly slam a wall down at 3.6 times 10 to the 52nd watts? What is so special about that number? It does not look special. It is not a round number. It is not 10 to the 50th or 10 to the 60th. It is this oddly specific value. Where does it come from? Why there? Why a ceiling at all? Here is the first clue, and it is a strange and wonderful one. That ceiling, 3.6 times 10 to the 52nd watts, is not measured. It is not something astronomers found by looking at the sky and noticing that nothing ever gets brighter than this. It is something that falls out of the equations of physics all by itself when you combine just two numbers, two of the most fundamental constants of nature. The first is the speed of light. The second is the strength of gravity, a number called Newton's gravitational constant, which measures how strongly mass pulls on mass. Take the speed of light, raise it to the fifth power, that is, multiply it by itself 5 times, and divide by Newton's gravitational constant, and out comes a number with the units of power. Out comes, almost exactly, our ceiling. Let me say that again, slowly, because it is the hinge of the entire story. You do not need a single fact about black holes, or quasars, or supernovae or candles to find this ceiling. You need only two numbers, the speed of light and the strength of gravity, two of the most basic constants in all of physics, the ones that show up everywhere, in everything. Combine them in this one particular way, and the maximum brightness of the universe simply appears. It is written into the constants themselves. It was there before there were any stars to test it. It was there before there were atoms. The ceiling on how bright anything can ever be was fixed at the moment the universe set the speed of light and the strength of gravity, which is to say, at the very beginning. This number even has a name. Physicists sometimes call it the Planck luminosity, or the Planck power, after Max Planck, whose name is attached to many of the deepest scales in physics. And there is a beautiful, almost eerie detail hidden in it that we're going to explore fully in 2 parts from now, but I will plant the seed here. Most quantities that carry Planck's name are quantum quantities. They involve the strange physics of the very small, but this one, the maximum power, does not. The signature ingredient of quantum physics is missing from it entirely. The maximum brightness of the universe is built from gravity and light alone, with no quantum mechanics required. That will turn out to matter enormously. But before we get to why the ceiling is missing its quantum ingredient, we have to answer the more basic question, the one that should be burning by now. We have established that the ceiling exists, and that it comes from just 2 constants. But we have not yet seen why. Why should combining the speed of light and the strength of gravity give you a maximum brightness? What is the actual physical reason that the universe refuses to shine any brighter than this? Why does the ladder stop here, and not somewhere else, and not nowhere at all? Before we get there, I want to sit for a moment longer with how unsettling this should feel, because it is genuinely one of the strangest facts in physics, and it tends to get rushed past. We are completely comfortable with the idea that the universe has a maximum speed. The speed of light is famous. Everyone has heard of it. It has been absorbed into culture, into science fiction, into ordinary conversation. But almost nobody has ever heard that the universe also has a maximum brightness, a maximum power, a hard ceiling on how much energy can be released per second anywhere by anything. It is just as fundamental as the speed limit. It is built from the same constants, and yet it is almost unknown outside a small circle of physicists. There is something wonderful about that. The idea that one of the most basic limits of reality has been sitting in the equations all along, largely unremarked, waiting for colliding black holes to come along and press right up against it before anyone paid much attention. And consider how recently this became more than an abstraction. For most of the time, physicists have known about the c to the 5th over g number. It was a curiosity, a combination of constants with the right units, interesting to write down but impossible to compare against anything real, because nothing we could observe came remotely close to it. The brightest things we knew about, quasars and supernovae, sat trillions of times below it. The ceiling was so far above the tallest thing in the room that it was purely theoretical. And then, in 2015, in a single morning, that changed forever. Suddenly we had measured something, an actual event in the real sky, that reached within a factor of 1,000 of the ceiling. The abstract number had a real neighbour at last. The most theoretical limit in physics suddenly had something pressing against it that we had heard with our own instruments. That is part of why this moment in science feels so alive. The wall stopped being a thought and became a place that real events visit. The answer is the most elegant thing in this entire story. It comes from forcing two of the greatest ideas in the history of science, two ideas you have already met tonight, to sit down together and agree. One of them limits how fast energy can escape. The other limits how much energy you can cram into one place. And when you make them shake hands, a wall rises up between them, exactly where it has to, at exactly the value we measured. In the next part, I am going to build that wall in front of you, brick by brick, using nothing but ideas you already understand. And by the end of it, you are going to see the maximum brightness of the universe, not as a mysterious decree, but as something that simply could not have been any other way. Let us build the wall. Part 7. How two theories build the wall. To build the wall, we need two ideas, and you already have both of them. The first comes from Einstein's special theory of relativity, and it is probably the most famous rule in all of physics. Nothing can travel faster than the speed of light, not matter, not information, not energy. The speed of light is the universe's ultimate speed limit, the fastest that anything is allowed to move. We're going to use this rule in a slightly unusual way, so let me frame it carefully. If you have a region of space, a volume, holding a certain amount of energy, and you want to release that energy, to pour it out of that region, then the energy cannot leave faster than light can carry it across the region. The size of the region sets a kind of minimum time. Energy has to physically travel out, and it cannot do so faster than light. So the bigger the region, the longer it takes, at minimum, to empty it. This is our first rule. Call it the escape limit. Energy cannot leave a region faster than light can cross it. The second idea comes from Einstein's other masterpiece, general relativity, the theory of gravity we've been using all night, and it is this. There is a limit to how much energy, or equivalently how much mass, you can pack into a region of a given size. Pile in too much, and the gravity becomes so intense that the region collapses into a black hole and seals itself off behind an event horizon. We have already seen this idea in action. A black hole is exactly what you get when too much mass is crammed into too small a space. So this is our second rule. Call it the packing limit. You cannot concentrate more than a certain amount of energy in a region before it becomes a black hole. Now watch what happens when we put these two rules together. They are about to build a wall. We want to make the brightest possible flash. Brightness is energy divided by time, energy released per second. So to maximize brightness, we want two things. We want as much energy as possible, and we want to release it in as little time as possible. Let us take each in turn, using our two rules. How much energy can we possibly have in our region? The packing limit tells us. The absolute most energy we can stuff into a region of a given size, right at the edge before it collapses into a black hole, is set by the mass that would form a black hole of that size. So the maximum energy is the rest mass energy of a black hole that just fits in our region. That is the most we can possibly have to spend. How fast can we release it? The escape limit tells us we cannot pour that energy out faster than light can cross the region, and the relevant size, the distance the light has to cross, is the size of the black hole itself, the radius of its event horizon. So the minimum time to release the energy is roughly the time it takes light to travel across the black hole from one side of the horizon to the other. So now we have both pieces. The maximum energy is the energy of a black hole that fills the region. The minimum time is how long light takes to cross that black hole. Divide the one by the other, the maximum energy by the minimum time, and you get the maximum brightness. The most power anything of that size can possibly put out. And here comes the moment of magic, the single, most beautiful step in this whole story. When you actually do that division, when you take the energy of the black hole and divide it by the light crossing time of the black hole, the size of the black hole cancels out, the mass cancels out, everything specific to your particular object, how big it is, how heavy it is, all of it disappears. What is left over is just a combination of the two fundamental constants, the speed of light and the strength of gravity. The speed of light to the fifth power divided by Newton's gravitational constant, the ceiling, 3.6 times 10 to the 52nd watts. The masses cancel. I want you to really feel what that means, because it is the deepest point in this entire video. It means the maximum brightness does not depend on what you are. It is the same for a marble and for a galaxy. If you took a tiny black hole the size of a grain of sand and let it release its energy as fast as physically possible, the most power it could put out divided by the time it takes gives you the same ceiling. If you took a black hole the size of a galaxy and did the same, you would get the same ceiling. A small object holds less energy, but it is also smaller, so light crosses it faster, so it can release that smaller energy in less time, and the two effects exactly balance. Less energy, but less time. More energy, but more time. The ratio, the brightness, comes out identical. The universe has one maximum brightness, and it applies to everything, equally, regardless of size, regardless of mass. The masses cancel. Let me make this physical with a thought experiment, so it lives in your body and not just in the equations. Imagine I hand you a dial. Just a simple dial, like the volume knob on an old radio, and this one is labelled in plain letters, brighter. You can turn it as far as you like. Your goal is to make the brightest possible flash, and I am giving you complete freedom. So you start turning. At first, it is easy, and it is fun. You turn the dial, and you pile in more energy, more mass, and the flash gets brighter. You turn it again, and you squeeze that energy into a smaller space, so it can come out faster, and the flash gets brighter still. You are climbing the ladder. More energy, tighter packing, brighter and brighter. You turn the dial harder. The flash blazes. You're passing supernovae, passing quasars, passing the merger. You feel like you can do this forever. You reach for the dial to give it one more big twist. And here, at the last turn, the universe does something you did not expect. You twist the dial to cram in just a little more energy, to squeeze it just a little tighter, to push the brightness just a little higher. But instead of getting brighter, the thing in front of you goes dark. Because you have crossed the packing limit. You concentrated so much energy in so small a space that it collapsed into a black hole and sealed itself off. The light you were trying to release is now trapped behind an event horizon, falling inward forever, unable to reach your eye. You did not make a brighter flash. You made a black hole, and it swallowed the flash. Turn the dial past the maximum, and the universe does not give you more light. It takes the light away. That is the wall. That is why it is there. It is not an arbitrary rule someone imposed. It is the meeting point of two limits that you cannot get around. Try to release energy faster, and you bump against the speed of light. Try to pack in more energy to compensate, and you bump against the formation of a black hole. The two limits close in from opposite sides, and between them there is exactly one maximum brightness, and you cannot get past it. The escape limit on one side, the packing limit on the other, and the wall standing exactly where they meet. And now you can see why the black hole merger came so close to the ceiling. Of course it did. A black hole merger is the universe pushing right up against both limits at once. You have the maximum possible energy, because you are working with black holes, the densest objects there are, and you are releasing it in the minimum possible time, because the whole thing happens in a final plunge that lasts only as long as light takes to cross the black holes involved. A merger is nature turning the dial all the way to the edge, right up to the last safe notch before everything goes dark. It is no accident that the brightest event we have ever measured is a collision of the very objects that define the packing limit. Black holes are not just things that happen to be bright, they are the universe operating at the absolute boundary of what is possible. So we have built the wall. We have seen that it comes from forcing the speed limit of special relativity to agree with the collapse limit of general relativity. We have seen that the masses cancel, that the ceiling is the same for everything, that it is woven from just two constants of nature. This should feel like a satisfying place to stop. The mystery is solved. The ceiling exists because of these two beautiful limits, and that is that. I want to make sure the logic of the two limits is fully settled in your mind, because it is the structural spine of the whole idea. So let me say it one more way, from a slightly different angle. Picture the two limits as two walls slowly sliding toward each other, trapping you in the middle. The first wall is the speed of light. It says, whatever energy you have, you cannot pour it out faster than light can carry it across your object. So if you want to release energy quickly, you must make your object small, because light crosses a small object faster. That wall pushes you towards smallness. But now the second wall slides in. It says, you cannot make your object too small for the amount of energy it holds, because if you concentrate that much energy in that little space, it collapses into a black hole and seals itself away. So that wall pushes you toward bigness. One wall pushes you small, the other pushes you big, and between them there is exactly one configuration that maximizes your brightness, one perfect balance point. And the brightness at that balance point is the ceiling. You're not free to escape in either direction. Go smaller to release faster, and you trip the black hole. Go bigger to hold more energy, and light takes too long to carry it out. The two walls leave you exactly one door, and that door is the maximum brightness. This is also, by the way, why a black hole merger is nature's perfect machine for approaching the ceiling, and it is worth seeing clearly. A black hole is, by definition, an object sitting exactly at the second wall, the packing limit, the densest that anything can be without already having collapsed further. So when two black holes merge, you begin with objects already at the maximum allowed density, and you release their energy in the minimum possible time, the time light takes to cross them, which is the first wall. A merger is the universe standing in the one doorway between the two walls and slamming it as hard as it can. That is why, of all the events in the cosmos, it is mergers that climb highest. They are not bright by accident. They are bright because they are built from the very objects that define the limit, operating at the very edge of what the limit allows. The brightest thing in the sky is the universe pressing on its own boundary with both hands. But it is not that, because there is something hiding inside this ceiling that, once you notice it, refuses to let you rest. It is a missing ingredient, a letter that should be in the equation and is not. And the absence of that one letter is going to take us out of the comfortable world of Einstein's physics entirely and toward the deepest unsolved problem in all of science. In the next part, I want to show you what is missing and why its absence is one of the strangest clues in modern physics. Let us go looking for a letter that should be there and is not. Part 8. The missing letter. There is a particular feeling that physicists chase, a feeling that something is wrong in an interesting way. It usually arrives as a small detail that does not fit, a number that is too round, a symmetry that is slightly broken, a piece that seems out of place. And one of the strangest of these small wrong-feeling details lives right inside the ceiling we just built. To see it, we need to talk for a moment about the family of numbers that physicists call the Planck scales, and the one letter that defines them. In the early 20th century, physicists discovered that nature seems to have a set of fundamental scales, deep-down units built from the basic constants of the universe. There is a Planck length, the smallest meaningful distance. There is a Planck time, the shortest meaningful interval. There is a Planck mass, a Planck energy, a Planck temperature. These are not human units, like meters and seconds, which we made up for our own convenience. They are the universe's own units, assembled out of the fundamental constants themselves. And here is the crucial thing about almost all of them. They are built using three constants: the speed of light, the strength of gravity, and a third one, the one that is the signature of all quantum physics, a number called the Planck constant, usually written as a little letter h, which sets the scale of the quantum world, the graininess of energy, the fundamental fuzziness of the very small. That little h is the fingerprint of quantum mechanics. Wherever it appears, you know you are in the realm of the quantum, the strange domain where particles are also waves, where energy comes in discrete packets, where certainty dissolves into probability. The Planck length has an h in it. The Planck time has an h in it. The Planck mass, the Planck energy, all of them carry that quantum fingerprint. They are quantum quantities, born from the marriage of gravity, light, and the quantum. And now look back at our ceiling, the maximum brightness, the speed of light to the fifth power, divided by the strength of gravity. Look for the h, look for the quantum fingerprint. It is not there. The Planck constant, the defining ingredient of all quantum physics, the letter that appears in every other Planck scale quantity, is completely absent from the maximum brightness. It cancels out. It is gone. The ceiling on how bright the universe can be is built from gravity and light alone, with no quantum mechanics whatsoever. And that is deeply, genuinely strange. It is a Planck quantity with the quantum taken out. It carries Planck's name. It sits at the most extreme scale imaginable, and yet it has nothing quantum in it at all. It is purely classical. It would exist, exactly as it is, in a universe where quantum mechanics had never been discovered, in a universe with no quantum physics at all. How do we know this is not just a fluke, a coincidence of how we happen to write the equation? Because the number has a history, and the history is older than quantum mechanics itself. Back in the 1880s, decades before anyone had dreamed of quantum theory, before Planck, before Einstein, an Irish physicist named George Johnstone Stoney was already playing with combinations of the fundamental constants. He was trying to build natural units out of the speed of light, the strength of gravity, and the charge of the electron, and buried in the combinations he could form was a quantity with units of power, built from the speed of light and gravity. The maximum brightness, or something extremely close to it, was sitting there in the mathematics in the 1880s. It predates the quantum revolution by a generation. Whatever this ceiling is, it is not a quantum effect. It is something more ancient and more basic than that, woven into the classical bones of the universe. Let me make sure the weight of this lands, because it is one of the emotional peaks of our whole journey, and it deserves to be felt slowly. This ceiling, this maximum brightness, was not invented by us. It was not even invented by the stars. It was fixed at the moment the universe set its two most basic numbers, the speed at which light travels and the strength with which mass pulls on mass. And those numbers were set at the very beginning, in the first instance of everything, which means the maximum brightness of the universe was decided before there were any galaxies to test it, before there were any stars to approach it, before there were any atoms at all, before there was anything in the cosmos except the freshly set rules themselves, and those very same two numbers, the speed of light and the strength of gravity, the two numbers that fix the maximum brightness, are also the numbers that built you. The strength of gravity is what gathered the gas that formed the first stars, the stars that forged, in their cores and their death explosions, the carbon and the oxygen and the iron that make up your body. The speed of light governs how every atom in you holds together, how every chemical bond forms, how every signal travels along every nerve. You're assembled, atom by atom, by the same two constants that, in a different combination, forbid the universe from ever shining too brightly. The rule that caps the brightest event in the cosmos, and the rule that built the cells reading meaning into these words are written in the same two numbers. You and the ceiling are made of the same law. There is something almost unbearably intimate about that, when you let it settle. We tend to think of the great cosmic limits as remote, abstract, out there, having nothing to do with us. The maximum brightness of the universe sounds like the most distant fact imaginable, a number relevant only to colliding black holes a billion light-years away. But it is not distant at all. It is built from the same constants that are right now holding your atoms together and pulling your feet to the floor. The most extreme limit in the cosmos and the most ordinary facts of your existence are not two different things. They are two faces of the same handful of numbers, the small print of reality, present everywhere, in everything, including in you. It is worth saying clearly what it would have meant if the quantum letter had been present, because the contrast is the whole point. If the maximum brightness had contained the Planck constant, we would shrug and say, of course, this is a quantum gravity effect. It belongs to the unknown physics of the very small. It only matters at scales we can never reach, and we would file it away with all the other things that live behind the quantum gravity door. We would not expect to ever see it in the real sky. But the constant is not there. The limit is classical. And a classical limit is one that belongs to the large-scale, smooth world we actually live in and observe. The world of orbiting stars and merging black holes and waves rippling across real space. That is why this ceiling is not a remote abstraction. It is a feature of the everyday large-scale universe, and it is exactly why a real, observable event like our merger could march right up to it. A purely quantum limit would hide forever at scales smaller than an atom. A classical limit stands out in the open, at the scale of colliding black holes, where we can watch things approach it. The missing letter is the reason the ceiling is visible at all, and there is a further twist that deepens the puzzle rather than resolving it. You might think a purely classical limit, one with no quantum in it, would have nothing to do with quantum gravity, the great unsolved marriage of the quantum and gravity. But it is precisely the opposite. The fact that this limit is classical, and yet sits at the most extreme scale imaginable, makes it a kind of bridge, a place where the classical and the quantum descriptions are forced to meet. The classical world hands you a hard wall, but says nothing about what is on the other side of it. To learn what happens beyond the wall, you would have to bring in exactly the quantum physics the wall left out. So the missing letter does not mean the quantum is irrelevant. It means the quantum has been pushed to the far side of the wall, waiting there, the hidden half of a story whose first half is written in pure gravity. We are going to walk right up to that wall in two parts and try to peer over it. So the missing letter is not a flaw, it is a clue. The fact that the ceiling is purely classical, that it carries no quantum fingerprint, is telling us something profound about where it comes from. It is telling us that this limit belongs to the smooth, continuous world of Einstein's gravity, the world of curved space-time and bending light, not to the grainy, probabilistic world of the quantum. And that raises a question that is going to drive the rest of our journey. We have two great theories of reality. We have general relativity, Einstein's theory of gravity and space-time, which is smooth and classical, and which built our ceiling. And we have quantum mechanics, the theory of the very small, grainy and probabilistic, ruled by that little letter H. For a century, these two theories have refused to fully agree with each other. They work beautifully in their own domains, but no one has ever managed to fully join them into a single theory of everything. That unsolved marriage is called quantum gravity, and it is the deepest open problem in all of physics. And here is where it gets remarkable. Our ceiling is built from gravity alone, with no quantum in it. But the ceiling is also, as we'll see, exactly the place where the quantum has to come back. Because if you try to imagine what physically happens to space-time itself when an event climbs all the way up to the maximum brightness, the smooth classical picture begins to break down, and the grainy quantum nature of space, the very thing the ceiling left out, comes roaring back into the story. The missing letter is missing from the ceiling, but it has been waiting on the other side of it the whole time. And before we walk up to that edge, there is one more thing the ceiling has to show us. A twin limit hiding right beside the maximum brightness. A limit not on how bright things can be, but on how hard the universe can ever push. Let us go and meet the maximum force. Part 9. The twin maximum force. The maximum brightness has a twin, and in some ways the twin is even more fundamental, even harder to wrap your mind around. To meet it, we just have to do something very simple to our ceiling. We take the maximum power, the maximum brightness, and we divide it by the speed of light. When you divide a power by a speed, what you get in the language of physics is a force. And so, sitting right next to the maximum brightness, derived from it by the simplest possible step, is a maximum force. Worked out carefully, this maximum force comes to the speed of light raised to the fourth power, divided by 4 times Newton's gravitational constant. The number it gives is about 3 times 10 to the 43rd newtons. A newton, for reference, is roughly the force you feel holding a small apple in your hand against gravity. So this maximum force is about 3 times 10 to the 43rd apples, a number so vast it has no meaning in ordinary life. But the value is not the point. The point is the claim. The claim is that this is the strongest force that can exist anywhere in the universe. No two objects by any means, through any interaction, can ever push or pull on each other harder than this. There is a maximum to how hard the universe can ever shove. Now remember where we started this part of the story, back at the very beginning of the wall. In Newton's universe, force had no limit at all. Push 2 masses closer and closer, and the gravitational force between them climbs toward infinity, with nothing to stop it. That was the reasonable-sounding idea that turned out to be wrong. And here, finally, is the precise reason it is wrong. The thing that saves the universe from infinite forces. The reason you can never reach an infinite force is that, long before you get there, something else happens. As you push 2 masses closer together to increase the force between them, you are concentrating mass and energy into a smaller and smaller region. And we know what happens when you do that. At a certain point, you cross the packing limit, and the region collapses into a black hole. An event horizon forms around the whole arrangement and seals it off. The force between 2 objects, just as they are about to touch in the most extreme way possible, reaches this maximum value, and then nature draws a curtain. You cannot push harder, because if you try, you make a black hole, and the question of pushing harder no longer even makes sense. In fact, that is the clean way to picture the maximum force. It is the gravitational force between 2 black holes of equal mass at the very instant their event horizons touch. That is as hard as gravity, or anything else, can ever pull. Right at that moment of contact, the force hits the ceiling, the speed of light to the fourth over 4 times the gravitational constant, and it can go no higher. The maximum force is the universe's way of refusing to ever divide by 0, of refusing to ever let a distance shrink all the way to nothing, and a force climb all the way to infinity. The black hole always forms first. The curtain always falls in time. This idea has a history worth telling honestly, because it is a lovely example of how science actually works, with all its tangles and corrections. The maximum force conjecture in its modern form was put forward in 2002 by the physicist Gary Gibbons. He proposed that general relativity contains this hidden maximum, this greatest possible force, equal to the speed of light to the fourth over 4 times the gravitational constant. Later, in 2014, Gibbons worked with another great physicist, John Barrow, on a paper they titled simply and beautifully Maximum Tension, exploring the idea further and asking whether it survived in a universe with a cosmological constant, the mysterious energy that drives the expansion of space. The idea of a maximum force, a greatest possible push, became a serious topic in the physics of gravity. The related power limit, the maximum brightness expressed slightly differently, is sometimes called the Dyson luminosity, after the famous physicist Freeman Dyson, and here the story takes a turn that I love because it is so human. Back in 1962, Dyson wrote a paper called Gravitational Machines, in which he worked out how much power a pair of stars orbiting each other would radiate as gravitational waves, exactly the process that decades later would produce the chirp we started with tonight. And he found that as the stars orbit faster and faster, approaching the speed of light, the power they radiate climbs toward a limit set by the speed of light to the fifth over the gravitational constant, our ceiling. So it would be natural to credit Dyson with discovering the maximum luminosity of the universe. Except Dyson himself refused the credit. Years later, with admirable honesty, he flatly denied having proposed any such universal law. In his own words, "It is not true," he said, "that I propose the formula as a luminosity limit for anything. I make no such claim." He had found the limit for one specific situation, two stars spiraling together, but he was careful, scrupulously careful, not to claim it as a law of the whole universe. The bolder claim, that this is an upper limit for the luminosity of any process anywhere in the cosmos, is usually credited instead to Kip Thorne, one of the architects of gravitational wave science, a man who would later share a Nobel Prize for the very detection we began with. There is something wonderful about that web of connections. The man who declined to claim the limit, Dyson, calculated it for orbiting stars. The man who did propose it as universal, Thorne, helped build the machine that caught two black holes radiating at nearly that exact limit. The theory and the detection, separated by half a century, were woven together by the same handful of people, and the maximum force carries forward the deepest property of its twin, the one we marvelled at 2 parts ago. Just like the maximum brightness, the maximum force does not depend on what objects you use. The masses cancel. It does not matter whether you're talking about 2 tiny black holes or 2 enormous ones, 2 specks or 2 galaxies worth of mass. The greatest force at the moment their horizons touch is always the same value, set only by the speed of light and the strength of gravity. The universe does not care how big you are. The limit is the same for everything, the marble and the galaxy, the smallest things and the largest. The masses cancel, again, here as everywhere in this story. There is a strange equality woven through it all. Whatever you are, however vast or however small, you are held to the exact same ceiling. The universe plays no favourites. There is one more detail about the maximum force that I find almost suspiciously beautiful, and it concerns the shape of our universe itself. The clean result, the speed of light to the 4th over 4 times the gravitational constant, with that tidy factor of 4, holds precisely in a universe with 3 dimensions of space. Our universe, length, width, and height, 3 directions. If you redo the mathematics in a hypothetical universe with more spatial dimensions, 4 or 5 or more, the clean limit falls apart. The tidy expression stops working. The maximum force, in its sharpest and most elegant form, appears to be a special feature of a universe that has exactly the 3 spatial dimensions that ours happens to have. Our particular geometry, the 3 directions you can point in, seems to be exactly the setting in which this ceiling is crisp and clean. Whether that is a deep clue about why our universe has 3 spatial dimensions, or just a curiosity, nobody can yet say. But it is the kind of detail that makes physicists sit up. The wall is sharpest in precisely the universe we live in. So now we have the full picture of the ceiling and its twin, a maximum brightness and a maximum force, both built from the same 2 constants, both with the masses cancelling out, both purely classical with the quantum fingerprint missing, both sharpest in our 3-dimensional universe, and both standing as walls that the most violent events in the cosmos, the colliding black holes, climb right up to and press against but never cross. It is a remarkably complete and self-consistent picture. The universe has a loudest it can be and a hardest it can push, and they are the same fact wearing two faces. I find the human side of this part of the story almost as moving as the physics, so let me linger on it for a moment. Here you have a limit that nobody quite wants to claim. Dyson calculates it for orbiting stars and then carefully says, "That is not a universal law. I make no such claim." The universal version gets attributed to Thorne. Gibbons proposes the maximum force, and Barrow joins him to test it. And to this day there is honest, ongoing argument about exactly what the limit means and what number sits in front of it. This is not a story of a single genius declaring a law from a mountaintop. It is a story of careful people circling a strange truth for decades, each one willing to say what they were sure of and, just as importantly, what they were not. There is a kind of integrity in Dyson's refusal that I think is worth admiring. He had every chance to attach his name to one of the most fundamental limits in physics, and he declined because the evidence he personally had only covered one specific case. That is what science looks like when it is working well. Not grand pronouncements, but scrupulous, patient, honest people refusing to claim more than they can show, even when the prize is enormous. And there is something fitting about the fact that the limit took so long to be taken seriously as a universal law, because it lives at a scale that, until very recently, nothing real ever reached. A law about the maximum brightness of the universe is only testable if the universe actually produces something that comes close to it. For most of the history of this idea, nothing did. The number sat in the equations like a locked room nobody had a key to. It is only now, in the era of gravitational wave astronomy, with detectors sensitive enough to catch black holes merging at nearly the maximum brightness, that the limit has stopped being a curiosity and started being something we can actually probe. We are, in a real sense, the first generation that can hear events loud enough to test the loudest the universe is allowed to be. The theory waited half a century for the instruments to catch up. Now they have. But we have been carefully avoiding the deepest question of all, and we can avoid it no longer. We know the wall is there. We know why it is there. We know it comes from gravity and light and the meeting of two limits. But we still do not know what actually happens at the wall. What does it physically mean to reach the maximum brightness? What is going on in space-time itself at that final notch on the dial, the last instant before the black hole forms and the curtain falls? It turns out that this question takes us straight to the edge of known physics, to the one place where the missing quantum letter finally comes back, where the smooth fabric of Einstein's space-time appears to tear, and where, just maybe, we get our first glimpse through the locked door. Let us walk up to the edge. Part 10. The Edge of Space-Time. We have arrived at the most mysterious place in our whole journey, the edge itself, and I want to approach it slowly, the way you would approach the rim of something very high and very deep. We know the ceiling is there, we know it sits at 3.6 times 10 to the 52nd watts, but knowing where a wall is not the same as knowing what the wall is made of. So let me ask the question we have been circling all night. What actually happens, physically, in the fabric of space, at the moment an event reaches the maximum brightness? What is the wall really? To even begin to answer, we have to recall the missing letter. The ceiling, as we found, is purely classical. It is built from gravity and light, with no quantum mechanics in it. That makes perfect sense in the world of Einstein, the world of smooth, continuous space-time, where space is a seamless fabric that can curve and ripple but never tears, never grains, never breaks. In that world, the ceiling is just a smooth limit, a value you approach and cannot pass, like a speed limit on an endless road. But here is the thing. We have very good reasons to believe that space-time is not actually smooth all the way down. We believe that if you could zoom in far enough, to scales unimaginably smaller than an atom, the smooth fabric of space would dissolve into something grainy, something quantum, something that froths and fluctuates. That grainy quantum nature of space-time is exactly what the missing letter, the Planck constant, would describe. And the deepest unsolved problem in physics, the marriage of gravity and the quantum that we call quantum gravity, is precisely the attempt to understand that grainy foundation. For 100 years, we have known we need such a theory, and for 100 years it has eluded us, because the places where it matters are so extreme that we can never reach them. The center of a black hole, the first instant of the Big Bang, energies our machines will never produce. The quantum nature of space lives behind a door we have never been able to open. And now, perhaps, you can feel the two halves of this story reaching toward each other. On one side, the maximum brightness, a purely classical wall built from smooth Einsteinian gravity. On the other side, quantum gravity, the grainy quantum nature of space, hidden behind a locked door. What if they are the same door? What if the maximum brightness is not just a limit within smooth space-time, but the exact place where smooth space-time ends, where the grain shows through, where Einstein's seamless fabric finally reveals that it was quantum all along? This is no longer idle speculation. In the last couple of years, a physicist named Wolfgang Wieland has approached this precise question using the tools of quantum gravity, and what he found is one of the most tantalizing results in recent physics. Wieland studied the quantum geometry of the light cone, which you can think of, loosely, as the quantum description of how a flash of energy spreads outward through space. And he discovered that something changes, dramatically, exactly at the Planck power, exactly at our ceiling. Below the maximum brightness, in his analysis, the power radiated by a system comes in discrete steps. It is quantized. It is grainy, just as quantum mechanics likes things to be, energy arriving in distinct packets rather than a smooth flow. But above the maximum brightness, above the ceiling, the picture changes character entirely. The neat discrete steps blur into a continuous flood, and the mathematics develops features, called caustics, that destroy the smooth, sensible, semi-classical picture of space-time altogether. The orderly quantum description simply breaks down. Space-time, in a sense, stops being describable as space-time. Let me put that as plainly as I can, because it is extraordinary. Wieland's work suggests that the maximum brightness is not just a limit on how bright things can be. It is the boundary of the describable. It is the point at which our picture of smooth, sensible space and time stops working. The seam where the classical world of Einstein gives way to the raw quantum chaos underneath. The ceiling may quite literally be the edge of space-time as we understand it, the place where one description of reality ends and another, deeper, stranger one would have to take over, if only we knew how to write it. I want you to come with me now, to that edge, and stand at the peak of the merger, and let me slow time down so we can almost see it. Imagine you are there, an impossible observer, watching two black holes in their final plunge. The power is climbing. We are passing the brightness of stars, of galaxies, of the whole visible universe, and still climbing, up toward the ceiling. Watch the fabric of space around the collision. At first it is smooth, curving violently but still smooth, still the elegant rippling fabric of Einstein. But as the power approaches the maximum, the fabric begins to change. It begins to shimmer, to lose its smoothness, to show a kind of grain, like a photograph enlarged until you can see the individual specks. The discrete, orderly steps of radiated energy start to blur and run together into a continuous roar. The sensible picture, the one where space is a smooth stage on which things happen, starts to dissolve in your hands. You're watching the description of reality itself come apart. You're looking through the seam, and then, before you can see what lies beneath, the black hole closes over it, the curtain falls, and the door is locked again. That is the weight I have been carrying toward you all night, and here, at the edge, is where I have to set it down. At the maximum brightness, our two greatest descriptions of reality stop agreeing with each other. Einstein's smooth space-time says one thing, the quantum nature of space says another, and the brightest possible event in the universe is precisely the place where they collide, the one natural laboratory where the deepest unsolved problem in physics briefly becomes real. Every time black holes merge somewhere in the dark, the universe runs the one experiment we cannot run, at the one energy we can never reach, and writes the answer in a language we cannot yet read, and then erases it before we can look. We live 1,000th of a step away from an answer that may be the most important answer there is, and we cannot quite get to it. The merger we detected climbed to within a factor of 1,000 of the edge. So close. And still, the door stayed shut. Now, I have to be honest with you, in the way this channel always tries to be, because the edge of physics is exactly where honesty matters most. Not everyone agrees that the ceiling is a perfectly clean, exact, inviolable law. The physicists Aidan Jowsey and Matt Visser, in 2021, reconsidered the maximum luminosity carefully and argued that the bound is more subtle than a single tidy inequality, that the exact factor in front, whether it is 1 or a quarter or something else, depends on precisely what you are measuring and how. Others, including Vito Cardoso and his colleagues in 2018, have examined and refined the idea from different angles. The honest scientific position tonight is this: the existence of a maximum brightness, somewhere right around 10 to the 52nd watts, is a profound and well-motivated feature of our universe. But whether it is an exact legal statute with a single perfect number, or a slightly softer scaling truth, a deep order of magnitude fact about the cosmos, is still being worked out. The awe and the uncertainty live side by side, and a thoughtful person holds both at once. The ceiling is real. Its precise nature is still a frontier. I want to address the temptation, which always arrives at moments like this, to leap past the honest uncertainty into something wilder. When people hear that the brightest events might mark the place where space-time tears, where our descriptions fail, it is tempting to spin that into grander claims. That black hole merges punch holes in reality, that they leak energy into other dimensions, that the ceiling is proof the universe is a simulation with a maximum render setting, like a video game that cannot draw anything brighter than a certain value. These ideas circulate widely online, and I understand their appeal because they take a genuinely strange truth and make it even stranger. But here is the thing I keep coming back to. You do not need the embellishments. The real, careful, mainstream physics is already more astonishing than the fan fiction. A maximum brightness woven from two constants, the same for a marble and a galaxy, sitting exactly where our smoothest theory of reality appears to dissolve into something we cannot yet describe, approached in the real sky by colliding black holes we have actually heard. That is not a watered-down version of the simulation story. That is a better story, and it has the additional virtue of being, as far as we can tell, true. The simulation framing, by contrast, explains nothing. A maximum brightness that falls out of relativity and gravity is exactly what real physics produces. It is not a clue that we are inside a program. It is a clue that the program, if you insist on calling it that, is just the laws of nature doing what they have always done. And the extra dimensions version is a good example of how the grounded truth outstrangers the fringe one. The fringe says maybe the energy leaks into other dimensions. The real physics says something more interesting and more disciplined. It says the clean form of the maximum force only holds in exactly 3 spatial dimensions, that our particular geometry is special, and that in a universe with more dimensions the tidy limit genuinely falls apart. That is a real, precise, dimension-dependent fact, and it is far more remarkable than a vague gesture at energy leaking away, because it ties the limit to the very shape of the space we live in. The lesson, again and again on this channel, is that you almost never have to reach for the fringe. The careful answer, the one the data actually supports, is usually the one that will keep you up at night. But notice that even the uncertainty does not diminish the wonder. Whether the ceiling is razor-sharp or slightly fuzzy, the central picture stands. There is a maximum to how bright the universe can be. It is woven from gravity and light. It is the same for everything, large and small, and it sits exactly where our smooth picture of reality appears to break down and hand off to a quantum description we do not yet possess. The brightest events in the cosmos are knocking on the door of quantum gravity, the deepest question we have. We have heard the knocking. We caught it in a machine in Louisiana on a quiet morning in 2015. We just cannot yet open the door. In the final part, I want to take everything we have found and bring it home, back to that silent chirp, back to the candle, back to you, and ask what it means to live in a universe that has a loudest it can ever be. Let us close the circle. Part 11. A knock on the door. Let us go back one last time to that quiet morning in Louisiana and to the chirp. When we first heard it, at the very start of tonight, it was a mystery. A faint rising note, 0.2 of a second long, softer than a bird call, registered as a shiver in the shape of space smaller than the heart of an atom. I told you then that it was the loudest sound the universe can make and that it was silent. And at the time, that was just a strange and beautiful contradiction. But now, having made the whole climb, you can hear that same chirp differently. Now you know what it was. It was 2 black holes, 3 suns of mass turning to pure energy, releasing power at 3.6 times 10 to the 49th watts, within a factor of 1,000 of the absolute maximum brightness that the laws of physics permit. It was an event pressed almost against the ceiling of reality, an event standing nearly at the summit of everything that can happen, knocking on the highest door there is. And it reached us not as light, not as a flash anyone could see, but as a faint stretching of space itself, the loudest sound the universe can make, and it is silent. That phrase means something else now, doesn't it? The silence is not absence. The silence is not the event being small. The silence is the sound of something so powerful that it bypasses light entirely, that it does not bother with photons, that it speaks instead in the language of space-time itself. The quietest thing we ever detected was almost the most powerful thing that can ever be. That is not a contradiction anymore. That is just what the top of the ladder sounds like, and think about what the climb taught us. We started with a candle, 1 watt, in a dark room, something you could cup in your hand, and we climbed. The light bulb, the city, all of human civilization, the sun, the blazing hypergiant straining against the Eddington limit, the supernova outshining its galaxy, the quasar devouring a sun every day, the gamma ray burst, the merger, 50 factors of 10, 50 multiplications, each one dwarfing the last, brightness leaping and leaping. And just when it seemed it would leap forever, just a few steps above the merger, the universe said its final word. Enough. Not because we ran out of mass, but because of something woven into the deepest structure of reality. The escape limit of special relativity on one side, the packing limit of general relativity on the other, closing in from opposite directions, leaving exactly one maximum brightness between them, 3.6 times 10 to the 52nd watts, fixed by nothing but the speed of light and the strength of gravity. And do you remember the most beautiful thing we found along the way? The masses cancel. The maximum brightness does not depend on what you are. It is the same for a marble and for a galaxy, for a grain of sand and for a black hole the size of the solar system. The universe has one ceiling, and it holds everything to it equally. And that same equality runs through the maximum force, the twin limit, the hardest the universe can ever push. Again the same for everything, again with the masses cancelling out. There is a kind of cosmic fairness in it. Whatever you are, however vast or however small, you are measured against the same wall. The candle and the colliding black holes are cousins, made of the same physics, held to the same limit, separated only by degree. And so are you. The same 2 constants that fix that ceiling also built the carbon in your hands and hold your atoms together. You're not a spectator to this law. You're written in the same numbers. But the deepest thing we found is not the wall itself, it is what stands behind it. Because the maximum brightness, that purely classical ceiling with the quantum fingerprint mysteriously missing, turns out to sit exactly at the place where our smooth picture of reality appears to break down, where Einstein's seamless space-time begins to shimmer and grain and dissolve into the quantum chaos underneath. The ceiling is not just a limit, it may be a doorway, the seam where the physics we know hands off to the physics we have spent a century failing to find. And the brightest events in the cosmos, the colliding black holes, are the only things in all of creation that climb high enough to knock on it. That is the image I want to leave you with, the one that has been waiting since the beginning. A knock on a locked door. We have been knocking on that door for 100 years, in our equations, in our theories, in our long search for a way to join gravity and the quantum into a single understanding of reality. And it turns out the universe has been knocking too from the other side all along. Every time black holes merge somewhere in the dark, the universe runs the one experiment we cannot run, at the one energy we can never reach, and presses right up against that locked door, and then seals it shut again before we can see through. We caught one of those knocks, faintly, in 2015. We're catching more of them now, year after year, as our instruments improve, each one another soft rap on the same door, another event climbing toward the edge of the describable. There is one more way to hold all of this, and it is the way I find most comforting, so I will offer it to you as the night settles in. We tend to think of limits as disappointments. A limit is a no, a wall, a closed door, a thing that stops you. And much of tonight has been about a limit in exactly that sense, the ceiling on how bright the universe can be. But turn it over, and a limit is also a kind of order, a kind of care. A universe with no maximum brightness would be a universe where, in principle, a single event could release infinite power, where there would be no flaw beneath the chaos, no rule that holds. The ceiling is not just a barrier, it is part of what makes the universe a coherent place rather than a runaway one. The same two constants that cap the brightness also keep the atoms in your body from flying apart, keep the sun burning steadily instead of detonating, keep the orbit stable and the chemistry gentle enough for life. The limits are not the universe being stingy, they are the universe being structured, being lawful, being the kind of place where a person can exist long enough to lie in the dark and wonder about colliding black holes a billion light years away. And so the maximum brightness, when you really sit with it, is not a cold fact about distant catastrophes. It is a quiet reassurance about the order of things. There is a loudest the universe can be, and because there is, everything quieter than that, which is to say everything, including you, including this moment, including the soft light in your room and the slow rhythm of your own breathing, gets to exist in the calm beneath the ceiling. The wall at the top of the ladder is the same wall that makes the bottom of the ladder, the candle, the quiet room, possible at all. The limit that forbids infinite brightness is the limit that permits gentle nights. And here is the quiet, hopeful truth to rest on. Right now, tonight, while you lie here in the dark, it is happening. Somewhere out in the universe, at this very moment, two black holes are spiraling into each other, faster and faster, shaking the fabric of space, climbing the ladder toward the ceiling, releasing more power in a few thousandths of a second than all the stars that exist. It is happening silently. It is happening invisibly. The ripples are already on their way, crossing the dark, and in some far future, a machine on some world may feel them arrive. A faint chirp, a shiver in the shape of space, another knock on the same locked door. The universe is speaking constantly in its loudest and quietest voice at once, in the language of space-time itself. We have only just learned how to listen. We do not yet know what is on the other side of the brightest possible thing. We do not know what the universe looks like beyond the edge where our descriptions fail. We do not know whether the door, when it finally opens, will reveal the grainy quantum foundation of space, or something stranger still that no one has yet imagined. That answer is out there, written over and over in the dark in every merger, at the one place we cannot quite reach. We live 1,000th of a step away from it. And maybe that is the most human thing about this whole story. To stand at the foot of a ladder that climbs from a candle to the edge of reality, to have climbed all the way to within a whisper of the top, to hear the knocking on the other side of the door, and to know, with both wonder and patience, that we are not there yet. But we are listening, and the universe, brighter and quieter than we ever imagined, is still speaking. So close your eyes, and somewhere in the dark, right now, two black holes are becoming one, and the light has a ceiling, and the door is waiting, and the universe goes on knocking softly in the language of space itself.